Always start with a quick visual inspection before performing any test. Check the mechanical supports, load cell orientation, and mounting surfaces for cleanliness, levelness, and alignment. Check load cells for dents, cracks, excessive wear in the loading area, bending, or buckling. Check the interconnecting cables at the summon box. All cabling should be free of cuts, crimps, corrosion, exposed wires, etc. Check the connection of the summon box to the digital indicator. Check the excitation voltage source connections. Ensure the excitation voltage source provides a stable signal. If visual checks reveal issues, correct these issues and determine if faults persist. If they do, proceed with troubleshooting the load cell. Before starting, there are a few things to consider. You will see 4-wire and 6-wire load cells. 4-wire cells have 2 input and 2 output and a shield wire. The 6-wire load cells use 2 extra wires known as sense or reference wires. These sense wires connect to the excitation wires at the load cell. This will compensate for any resistance changes in the wiring to the load cell due to changes in temperature. 6-wire load cells can be cut to length, but 4-wire load cells must never be cut because the excitation lines have internal resistors to help compensate for temperature changes, and cutting the cable will affect the calibration. Before starting a load cell test, make sure to have the specific load cell's spec sheet. The things you will need from the spec sheet are cable color code for proper wiring and testing purposes, full-scale output, the output resistance, and input resistance. These are for testing the resistance between the signal wires, which is the output, and excitation wires, which are the input. The insulation resistance. This is for testing for moisture ingress, and you must have a mega ohm meter for testing this resistance. And if listed, a zero balance spec. Not all cells list a zero balance spec. A zero balance test can help determine if the load cell has been subjected to any physical damage such as an overload, shock load, metal wear, or fatigue. And you must make sure the load cell is in a no-load condition before starting. This may require using a forklift to lift the scale or a jack to take pressure off of the cell. The full-scale output is attained by taking the excitation voltage and multiplying by the full-scale output on the spec sheet. So in this example, we got 5.013 multiplied by the 3 millivolts would be a 15.039 millivolt at full-scale capacity. If the spec sheet does not list a zero balance spec, taking the excitation voltage reading multiplied by the full-scale output will give the maximum cell output. Take this number and multiply by 1% to find your zero balance tolerance. All the weight, including the dead load, has to be removed from the load cells. With the cells powered up, measure the excitation voltage and write it down. Next, measure the millivolt output. Always add a force to the cell to make sure it is active. Record the zero balance reading. The common value for zero balance shift is 1% of maximum scale output. When performing the field test, remember that load cells can move up to 10% of full scale and still work properly, as long as the unit can reach its full capacity, have repeatable weighments, and return to zero. If not, the cell should be replaced. This test requires a mega ohm meter. Caution: never use a voltage higher than 50 volts DC to measure insulation resistance on load cells. An insulation resistance test is carried out when there are unstable readings and/or random changes in the zero balance point of the load cell. It measures the resistance between the load cell body and all its connected wires as follows. This is not a mega ohm meter. This is being used as a demonstration only. First, disconnect the load cell from the sum and boxer indicator. Connect all the input, output, and sense wires if equipped together. Measure the insulation resistance between the connected wires and the load cell body with a mega ohm meter. Next, measure the insulation resistance between the connected wires and the cable shield. Lastly, measure the insulation resistance between the load cell body and the cable shield. The insulation resistance should match the value in the product's load cell data sheet. A lower value shows an electrical leakage caused by moisture or contamination. A very low value indicates a short circuit giving unstable load cell outputs. If you do not have access to a mega ohm meter, you can also find if a cell has moisture by removing one cell from the J-box. And if the scale stables out, then this cell likely has moisture and needs to be replaced. Never try drying out the cell even though it may work. It will only last briefly because once moisture has penetrated the wire or the cell, it will continue to do so. Replace the cell. Before testing bridge resistance, disconnect the load cell. Find your spec sheet and look for the color code and the output and input resistance specs. Find the positive and negative excitation leads and measure across them with a multimeter to find the input resistance. If the input resistance check is within specs, test the output resistance across the positive and negative signal leads. Next, connect a lead to the shield wire, then take the other probe and go to each input and output wire. The reading should be OL. If any other reading, then it is leaking to the shield and the cell should be replaced. Even if the overall output resistance test was within normal specification, the load cell could still be damaged. Perform a full symmetry test. Let's call the first test A. You'll take positive excitation to negative signal. Then you'll go positive X to positive signal. These two readings should match within 1 ohm. Test B is negative excitation to negative signal. Then negative excitation to positive signal. These two readings to match within 1 ohm. The 2A readings must match and the 2B readings must match, but A does not have to match B. If errors are found, chances are there is a broken or shortened wire that could have been caused by a shock load, vibration, wear, or temperature extremes. For the shock test, if using a hammer, make sure it is a rubber mallet only. Do not use metal hammers when doing a shock test. With the cell or cells connected to the excitation terminals and the signal wires disconnected, put the multimeter probes on the positive and negative signal wires for the cell to be tested. Next, lightly tap on the load cell with a small rubber mallet or your hand for smaller cells to mildly shock it. Exercise extreme caution not to overload low capacity cells. Watch the readings during the test. The readings should not become erratic. They should remain reasonably stable and return to original readings. Continue until all cells have been tested.